Without this formal addition of the coenzyme A, it will be very hard for it to act as a substrate for further catalysis. Acetate, per se, um, without the coenzyme, would hardly enter the citric acid cycle. So that's the one of the major importances of the coenzyme A. And furthermore, we need to understand later on in the energetics part of it that it was reduced from pyruvate. So energetically speaking, these reactions randomly go through exergonic stages to endergonic stages. You might imagine, you might believe that when we're eating, all of the energy stored in it are going to be highly exergonic, and that's not true. A fair amount of reactions, in particular, we had seen step 6 from glycolysis. The reduction of acetate to coenzyme A is an energonic reaction. The formation of acetyl coenzyme A and the reduction of NADH plus H molecules are endergonic reactions because there is some form of energy investment, right? So in terms of enthalpy, we're going to see this next week when we measure and quantify the amounts that randomly they go through some endergonic stages and some exergonic stages. Okay? And there is a good reason for that. Now, step 3, step 4 yields 2 NADH molecules each. So here is already 4. Okay. Step 5, moving into step 6, yields 2 FADH2 molecules. Step 7 into 8 produces 2 more reduced electron carriers of NADH. All of these are being quantified there only in number. We still have to look at the efficiency of them in terms of quantifying the number of ATP molecules that were produced in the in the electron transport chain, and finally the chemiosmotic mechanism. Any questions? Clear enough all of these steps? Okay. All right. Now, finally, these electron carriers will soon enter the electron transport chain, which happens in the mitochondrial membrane. Membranes, you may recall, some of them are semi-permeable, some of them are fully permeable, which means that due to diffusion and osmosis, which are 2 major processes of transport, may allow for the movement of molecules in and out of the membrane. The difference between active and passive transport is based upon energy investment. If there is a movement from an area of high concentration to an area of low concentration, without the expenditure of energy, we classify that process or transport process as diffusion. But in some instances, as already seen in photosynthesis and now respiration, we see that these membranes at some point may induce the expenditure of energy. Hence, we classify them as semi-permeable. And the reason for that is because they allow certain materials to go from one area of low concentration to an area of high concentration to create, in this case, a proton gradient or a proton imbalance. Okay? This proton gradient, we'll see later on, is regulated by the huge enzyme complex by the name of ATP synthase, which then is internally kind of predetermined by our own metabolism. There is a high amount of physical exercise, burning a lot of energy, burning a lot of kilocalories or calories in general. Then the electron transport chain is activated to continue provisioning for those proton gradients. So in the enzyme complex number 1, NADH plus H releases those hydrogen ions. And those hydrogen ions will be actively transported by the transfer of electrons from NADH plus H to unit 1 of the electron transport chain. It's a form of active transport because energy is invested for this transport system, so that these hydrogen ions can move from an area of low concentration, which is the mitochondrial matrix, into the intermembrane space. That flow of energy allows for energy expenditure, and it comes from the oxidation of NADH plus H. So now we see the formation of a proton imbalance or a proton gradient where the mitochondrial matrix remains with low hydrogen ions, and the inside or the intermembrane space is fully loaded with hydrogen ions, making it strongly acidic. This notion is regulated, like I said before, by the concept of energy expenditure or metabolism. There's a lot of physical exercise, movement of the body, high respiration rates, sweating, etc. All of these does create this proton or regulates this proton imbalance, causing more of these NADH and FADH2 molecules as seen in molecule 2 being utilized for energy. In step 2, FADH2 molecules release their electrons, become oxidized, providing the hydrogen ions to go through the protein complex number 2. Again, it creates a proton imbalance. Once there is, the same thing happens here with the electrons being transferred to unit 3 and 4, causing more of these ions to move from the outside, from the mitochondrial matrix to the inside in the intermembrane space by the expenditure of electrons. So now under high concentration, there must be some form of regulation, which would allow a particular protein complex, which serves as a one-way transport system for hydrogen ions. In other words, hydrogen ions could not go through the ATP synthase from the mitochondrial matrix into the intermembrane space. That would not happen. Okay? So due to passive transport, majority of these ions go through that particular enzyme complex, the ATP synthase, creating now a positive proton gradient into the mitochondrial matrix. so that now these hydrogen ions can be fully utilized to produce a hydrolytic reaction, which means that these hydrogen ions can combine with oxygen to form water, as seen here, right? As seen in this particular section here. Hydrogen ions are bonded up with oxygen, forming water, which then serves as the final electron acceptor. Okay? I did make mention last class that these water molecules can be used and reused by plants to release off the electrons that were stored in water due to photolysis and can create supply the original electrons in the process of photosynthesis. So this chemiosmotic mechanism is very similar to the one seen in photosynthesis, except for one, right? The number of molecules that were present, the enzymes and so on. But most importantly, where the electrons come from in both of these reactions. One, in photosynthesis, it comes from the photolytic reaction of water, which means that the use of sunlight was used to break down water molecules to release the electrons into the reactions. In respiration, these electrons came from NADH and FADH2. So that's the importance of these molecules in respiration. They were not directly transmitted into ATP molecules because that could be a highly reactive procedure that could possibly degenerate the mitochondrial cells, organelles within our cells. Okay, so very interesting. So that is the process of the chemiosmotic mechanism, the electron transport chain, added up together. That's the process that they all undergo in the process of aerobic respiration. Any questions? Guys, you have any questions?
No, sir.
Clear enough? Good. All right. Like I said, I don't want to get into the energetics part of it yet. We are going to leave that for next week. Tomorrow, like I said, we want to do the presentations in the morning. And in the afternoon, we want to continue with glucogenesis. I will post the information, but I will still want you guys to read glucogenesis for me, okay? That's how it's being spelled here. Glucogenesis, right? So can you do that for me? And then we should finish up with aerobic respiration. Following that, we want to do the fermentative reactions, either the heterolactic or homolactic fermentation reactions, okay? And with that, we should finish up respiration and photosynthesis. And hence, all we're gonna be left with is, again, energy transfer in ecosystems. But this time around, sorry about that, we're hoping to do the quantification of energy as they move up through different trophic groups. All right. Well, guys, if you don't have any questions, any comments, concerns, that's going to be it for today. All I wanted is to finish up here discussing again, making sure that you understood, hoping you did. Tomorrow we should have a short quiz only on the electron transport chain and chemiosmosis, right? Okay, guys, I should see you tomorrow then. Take care.
Okay, bye, sir.
Okay, thank you.